we're going to do a few examples here to help us understand what we're talking about in this rigid body motion. So in order to start out, let's look at the motion of this pulley system. So I've got two rigid bodies. This one has an inner that's attached to the outer. And then I've got this wheel, and we're going to rotate this wheel, which is going to ultimately cause this pulley to turn. So what we're going to try and do here is at the instant when we're given an omega or our angular velocity, and we're given that it's 5 radians per second, we're also told that it's got an angular acceleration of 0.8 theta, where theta is in radians, and we want to determine the magnitude of the acceleration of point B when when A has rotated 3 times. So what we're going to look at is we're going to look at that acceleration of B, and the type of acceleration that we're going to look at is this one right here. So when we start out, we know that we've been kind of given this kind of a relationship that we've got the integral of our angular velocities is going to be related to the angular acceleration and the change in angle, and we've been given that our relationships that we have for these inner and outer circles. So we want to make sure that we have that. So we know we're going to get that rotation, we know we're going to get that pull. So now as we start working the problem, it becomes almost a plug and chug, but we have to understand that actual motion. So here I've got my two integrals. We're going to evaluate them at the conditions that we're given. We started at 5 radians per second. We want to know where we end up when we're at A, and we're told that we've got to go through A. So let's go ahead and do the evaluation. Let's do the integration, and we ultimately come up with our angular velocity after that time frame, omega A. We've got the response there. Well, now we've got to know we were asked as the angle changed 3 revolutions, right? That's where we were at. So we need that in radians. And that's one of the places that you need to make sure that you're in the right units, that you're working with those right units to get there. And so we can do that evaluation. We can evaluate our angular acceleration. We can evaluate our angular velocity, and we can come up with those values. Then we're going to use this relationship between our wheels or our pulleys in order to determine how C is moving. So we get our angular velocity of C is related to our changes in our size here. And we determine that it's 21.98 radians per second. We're going to do the same type of an analysis for our angular acceleration, and we end up with 6 pi radians per second. Now, we're asked for that acceleration at B, and so we're going to have to account for size at B, and because I want to be in meters per second and in meters per second squared, I need to make that conversion between millimeters and meters, which is exactly what I've done here, and we're just going to put in our values that we've already determined and calculated and to come up with the actual acceleration at point B. So it gives you a feel for how these problems are going to kind of work. So let's do another one, except this time we've got a gear problem. We're going to use the same kind of analysis that we just did. We've got a motor gives gear A the angular acceleration, where theta is in radians. We know our initial angular velocity, and we want to determine the angular velocity of gear B, and this is my gear B, after A undergoes 10 revolutions. So stop and think for what's going to happen in the motion. As A rotates this way, we're going to get a push on this gear, and this gear is going to rotate in that direction. So we're actually going to get a rotation in this direction. We know that this is 10 revolutions. I can't work a problem in revolutions. I need to be in radians. So I'm going to go ahead and make that conversion right away. We already know how we're going to approach this problem, and we're going to do it just like we did in the previous problem. We're going to go ahead and do our integration, do our evaluation. We plug in where we are with our change in angle, and we determine what our angular velocity of A is. Once we have that, we can go ahead and make that change because we know these radiuses, and we can come in and we can calculate the angular velocity of gear B, after we've gone 10 revolutions, and we know it's going to be 21.9 radians per second. So let's expand this just a little bit more, use a little bit different information. So this is Hibbler problem 1625. We've got a motorboat, that we've got a propeller, and we want to know what's happening at the tip of this propeller. Okay, we want to know it. So the motor is going to turn A is going to turn B, and B ultimately turns the propeller. Because this is 625, you know how the problems work in this book. This is a related problem to 1624, and 1624 actually gave us some information that the angular acceleration is 400 t cubed, and we're given the dimensions of RA and RB. So this time we're going to use a slightly different approach. We're going to look at our change in angular velocity as it's related to time, not to angle, because that's what we had done previously. And we're going to go ahead and evaluate that at our given A. And so we can get our angular velocity of A and our angular acceleration of A. And then we know what we're going to have to do next. We're going to have to relate that to the motion of B. So we know these that we've seen initially, because one of the things is we have to know the angular velocity of B, and we have to know that angular acceleration of B, because this is ultimately going to give us the information that we need to find out the motion at point P. So we could go ahead and do our calculations and plug that in, and we find out that we're at 13.18 radians per second for my angular velocity, and my angular acceleration is the 70.31 radians per second squared. Now, remember that I can do a linear velocity related back to our R times the angular velocity, and now we're going to use this B to tell us more about what's happening at P, so we can actually do that calculation. And initially I've done this in inches per second, and you'll see that down below I'm going to go ahead and make that conversion to feet, because our common units are feet per second and feet per second squared, and we want to get that acceleration of P, and we want it to be in feet per second squared. So I'm going to have to do my two components of my acceleration, and I'm going to go ahead and convert the 2.2 inches to feet, because there's 12 inches per foot, so that I can get those feet per second squared. I do that, and I ultimately calculate that the acceleration of point P is going to be 34.4 feet per second squared. Hopefully these three problems will get you started and get you helping to go in that first section of chapter 16, and we'll continue to see other examples.